Okay, so now we're going to talk about compound inequalities. Compound inequalities are a little bit more interesting. If something is a compound sentence, it's two phrases joined, actually not two phrases, two complete sentences joined together by conjunctions like and or. And we'll only be using the and or conjunctions in math for now. So if we think about a math equation, that's a sentence. So if we take a conjunction, we're going to take two math sentences and join them together with and or. And so when we do that, we'll end up solving inequalities that are really two separate inequalities and looking at them together as a set. So let's talk about sets. Sets are groupings of objects. When we talk about, so let's write that down, grouping of objects. Some of the sets that you know about right now are the set of real numbers, the set of integers, the set of even numbers, the set of rational numbers, the set of irrational numbers, the set of whole numbers. Those are sets. But there are also sets like the set of band students, the set of North students, the set of students in my class, the set of students in third period, the set of students in fourth period, and so on. So any grouping of objects. Now when we have so many sets out there in the world, it might make sense to talk about the intersection and the union of sets. So when we do that, I'm going to create two different sets, and we'll look at how they are the same and how they are different. So in our first set, we might have the set of, let's see, what should we do? The set of prime numbers. And the set of prime numbers would be in green. And so the first prime number is 2, and then we have 3, and then we have 5, and 7, and 11, and 13, and 17, and 19, and so on, dot, dot, dot. And in our other set, we're going to have numbers that are even. So that's 2, 4, 6, 8, 10, 12, 14, and so on. Now notice how I put 2 in the overlapping part of the sets. That's called the intersection of the sets. So if we talk about the intersection of the two sets, the intersection of these two sets only contains the element 2, because that's the only number that's in both prime numbers and even numbers. So this is prime numbers, and this is even numbers, and the only thing that belongs in both sets, can say I'm in both, is the number 2. Now when we talk about union, the union is any number that's in either set. So a lot of times we just shade the whole thing. And so this would be in either set, meaning any requirement. So it's either prime or even. Now notice the words we've used on intersection. We used or. And so or is something that goes with intersection. Or means we're intersecting the two sets. And is like both. I'm sorry, back that up. Or is a union of the two sets. It's both. Any. In any set. And the intersection of two sets is the element that is found in both sets. So the word might be both, or it is a prime number and it is an even number. So that's why 2 is the only number that falls in that set. Intersections of sets tend to be smaller numbers because it's a little bit more exclusive, while a union tends to be a larger number of elements because it includes anything that's in there. And so when we have a compound inequality, what we're doing is we're looking at two different sets that are joined by either a union or a set that is joined by intersection. And so remember that our union is or, and our intersection is and. Now let me throw these symbols up here. The intersection is the upside down U, and the union is the right side up U, and those are the symbols that we use. Okay, pause the video if you need to take notes on this terminology. Now we're looking at compound inequalities, and our first compound inequality we have is this example that we're going to do. And our steps are to graph each part, each side of our compound inequality, look for the intersection of the union of the graphs, and then complete the shading in a new graph. So in this first problem, I'm going to do the left side first, and do that in green. So I'm going to do x's less than or equal to 3. So here is my 0, 1, 2, 3. I'm going to circle my critical point. The values of x that are less than or equal to 3 are in this direction, and 3 is part of that solution. And I'm going to union that with values that are on this side, which I'm going to do in blue. X is greater than or equal to 4. So here's 4. I'm going to circle my critical point, and I'm going to shade this direction, and this critical point will be shaded. And so my final answer really is this entire number line right here that's been shaded. Everything except the interval between 3 and 4 is part of our solution. Okay? Take a minute, write down that example. Pause if needed. Next, I'm going to go through the next example, which is an intersection example. So let's move this one over, bring this one down. I'm going to graph the left side again in green. So I'm looking for x's that are less than or equal to 3. Here's 0. Here's 3. Put a circle around 3. Shade in the less than direction, numbers that are less than. Now using blue, I'm going to find the numbers that are greater than or equal to -1. Here's -1. I'm going to take blue and circle it. Shade this direction with blue. Shade my critical point. Now you can see this time we definitely need another number line because we need to find the spots that are in both sets, the places that have been shaded twice. So what that means we have to do is we have to look anywhere there's double shading. So I'm looking here along my shading, and I see that from left to right, it's only green until it gets to -1. And at -1, it's both green and blue because it's a critical point that's been shaded, and it's shaded by the green line. So I'm going to include -1, and it's double shaded all the way to 3. And again, that is shaded by the critical point as well as the line. And so my final solution are the values of x that are between 3 and -1. So when we get our graph, it's very easy to write our inequality as what we call a 3-part inequality because it shows x is greater than or equal to -1 and x is less than or equal to 3 altogether. Also note that if we were to do interval notation, we would go from -1 to 3 with our closed brackets, which is also quite easy to do once we see our graph. Our final solution is not this graph up here. This is our working graph. This is our final solution. Pause the video as needed to take notes. Now we're going to solve a compound inequality with OR. We're going to do basically the same thing we did before. We're going to graph one inequality and then the other, and then we're going to look at the combined. So this time we're going to look at x minus 4 is greater than or equal to -7. I can't graph that yet, can I? I actually have to do some work first before I can graph it. I'm going to solve this inequality. I'm going to add 4 to both sides. I get my 0 pair. X is greater than or equal to -3. And so now I'm going to graph that on my number line. Here's 0, 1, 2, -3. Circle my critical point. Graph it in x is greater than -3 direction and shade that critical point. And I've graphed and solved that inequality. Now I need to do the other one. I need to solve this one as well. I'm going to subtract 1 from both sides. X is less than or equal to 3. So now I'm going to graph this in blue on my number line 0, 1, 2, 3. I'm going to circle the critical point of 3. I'm going to shade in the less than direction. I'm going to shade my critical point because it is less than or equal to. And now we're looking for OR. Now for solving this inequality, if we look at OR, we see that any and all of the number line has been shaded by either one color or the other. So the solution of this problem really is all real numbers. And if we were to draw it on the number line, we would shade the entire number line, and that would be our solution. Okay, so I'm going to back this up a little bit, and we're going to look at how this thing changes a bit if we were changing that and to an or. That or to an and. So if we do that, we would still solve the two inequalities, but we would write and between them. And when we graph them, here's our -3 shaded this direction. And here is our 3 shaded this direction. Oh, I'm sorry. And those endpoints are part of our solution. Remember, when it's and, we're looking for what's double shaded. So we would be shading from -3 to 3. And as we go from -infinity to -3, it's only shaded by blue until we get to -3. Then it's green and blue, all the way to 3, green and blue. And we would write this three-part inequality solution as x is between 3 and -3. Now we're going to talk about three-part inequalities. Three-part inequalities, here's our first note, are only for ands. You don't do a three-part inequality with or. So that's our first thing we need to know. Anytime you have an and three-part inequality, you should be able to write inequality, compound inequality, you should be able to write as a three-part inequality. For example, if I have x is greater than or equal to 3 and x is less than or equal to 5, then I should be able to put that together to where x is in the middle and I have 5 and 3 on each side. And the way we do that is we always write from least to greatest. So we start with our smallest number, have a less than or equal to less than or equal to sign, our variable, another less than or equal to or less than sign, and then our largest number. Okay, so least to greatest, we always have our inequalities, our less thans, and we always have our variable in the middle. Okay? So what we had to do here is we had to turn this guy around. 3x, and remember x has the biggest side pointing towards it, so that's how we had to write it this time. And then we put that together with this one, and since we have 3 is less than or equal to x and x is less than or equal to 5, we can just put that together as 3 less than or equal to x less than or equal to 5. Similarly, if you have a two-part inequality that's all together, a three-part inequality that's all together, you can break that up, and all you have to do is repeat your x. So this is 3 less than or equal to x and x less than or equal to 5. And so you can break that up and split it into two different problems if you would like to do that. But remember, it's always and on a three-part inequality. You can't do it with ors, and your inequality signs have to be facing the same direction, and we like them to be less thans or less than or equal to's. We don't like greater thans because then the numbers are going opposite the way our number line is going. I hope this discussion helped you. Please make sure you've taken good notes, and we'll be talking about it in class as well.